Okay, everyone. So now we're going to begin my most favorite part of the next of our 14 hours together, and that is trig. So we divided trig into 3 sections here, okay? This first section is an intro to trig. So we're going to deal with radian measure, we're going to deal with arc length, and we're going to deal with the equation of the unit circle and build the unit circle. The second part of trig will deal with graphs and transformations of trigs. And then the last part of trig will deal with identities and equation solving, okay? So as I've said in a previous video, trig is heavy, okay? It accounts for almost a third of your mark. So we want to spend some time on it. It's usually the thing that stresses kids out the most. So we want to spend some time on it this weekend together. And really make sure you're super comfy, okay? All right, so to start off, we're gonna talk about radian measure. Radian measure is a more exact way of measuring a rotational angle. So before grade 12, when we were looking at angles, we would always talk about degrees. The problem with degrees is it's completely arbitrary. The Babylonians decided to take a circle and divide it into 360 parts. And then they just randomly decided to call one of those parts a degree. There was no mathematical basis for how a degree came to be. In math, when you get into deeper levels of math, everything you do needs to have a reason. There needs to be some sort of mathematical background for what you're doing. And so we had to create a new system to measure angles, and that new system is called radian measure. Now, the way radian measure works is you have a circle, and it ends up being the ratio of the arc length of the circle divided by the radius. So if that was the center of the circle, this is the arc length out here. So it's the distance around the outer edge of the circle, a piece of the whole circumference, if you will. And so if I took my arc length and I divided by the radius, that would give me the measure of this angle, theta, in radians, okay? Now, we say that that arc length is subtended by this angle, okay? That word subtended just means it's within the parameter of what that angle creates, okay? I don't want you to get confused about the word subtended there. And we have this conversion factor. Oh, sorry, by the way, theta equals A over R is on your formula sheet. But the other thing you have to understand with that is this is the definition of radian measure. So often they will ask you to use this formula, but they'll give you a degree measure. You can't put a degree measure in here. You'd have to convert that to radians first, okay? So you have to understand that this only works when we're in radians. And then we have a conversion factor. Pi radians is the same as 180 degrees, okay? Pi radians is the same as 180 degrees. So essentially, when you go to convert between degrees and radians, either you're going to multiply by pi over 180 or you're going to multiply by 180 over pi. And it just all depends on which direction you're going, okay? Saying pi radians is the same as 180 degrees. It's just like saying 1 inch is the same as 2.54 centimeters, okay? It's just a way to relate one system of measure to the other system of measure. Okay, so what I'd like you to do is convert the following measures to radians. So like I said, either you're going to multiply by pi over 180 or 180 over pi. Which one's going to work for this guy? Well, it's the pi over 180 because you want your degree symbol to divide out, okay? So we multiply 270 by pi over 180. And essentially what you do is you just ignore pi there. You go 270 divided by 180 and get a reduced fraction. That reduced fraction is 3 over 2. And so your answer is 3 pi over 2. We answer with pi included. We answer an exact value, okay? Another just quick little note as we're talking about this. It's super, super important. If you are talking about degrees, you have to put that little degree symbol there. If you do not have that degree symbol there, it is assumed you're talking in radians. And 270 radians is way different than 270 degrees, okay? All right, try 315 degrees. So we're going to multiply it by pi over 180. We're going to take 315 over 180 and reduce it. And that should give you 7 pi over 4. And then 626 degrees. Again, I'm just going to multiply by pi over 180 and then reduce it. We end up with 313 pi over 90. 313 pi over 90. Okay. Again, just like in the other videos, the answers may be popping up a little too quick for you. I'm not necessarily giving you time to work in the video, so just make sure you pause the video, try it yourself, and then keep going. Okay, now let's go the other way. Convert the following measures to degrees. Round to the nearest hundredth when necessary. So now we're going to take pi over 4 radians, and this time instead of multiplying by pi over 180, we're going to multiply by 180 over pi. In this first example, the pi's will actually divide each other out, and I'm just left with 180 over 40, sorry, 180 over 4, and that ends up being 45. Okay, so 45 degrees. And then negative 7 pi over 3, same thing. We're going to multiply by 180 degrees over pi. And that should end up with negative 420. And then this last one I like to throw in just as a conversation. There was no pi in the question because this is not an exact, this is just not an exact value using pi question. So what that means for you is when you go use this in your calculator, you actually have to press pi, okay? You'll have to go 180 and divide, so times by 180 and divide by pi, okay? And that's gonna give you 315.13 degrees, 315.13 degrees. Okay, determine an arc length subtended by 30 degrees and a radius of 5 centimeters. So there's that word subtended. It just means that this would be the 30 degrees and this would be the arc length there, okay? Leave your answer in terms of pi. So I can't use 30 degrees because that is degrees. I need to use radians, but I'm just gonna call that 30 pi over 180. As soon as I call it 30 pi over 180, I've now converted it to radians. It's not reduced, but that's okay. I can reduce it as I go. So 30 pi over 180 is the arc length over the radius, and I know the radius is 5. So now I'll multiply both sides by 5, and then I can reduce my fraction, and I end up with 5 pi over 6. Okay, so 5 pi over 6 centimeters would be the arc length there. Okay, determine the measure of the angle to the nearest degree if a radius of 1.8 meters subtends an arc of 50.2 meters. So this time you have the arc length and you have the radius, and you know that the theta, the angle, is your arc length divided by your radius, but that's going to give me the angle in radians. So then I'd have to convert it to degrees because I was asked for degrees. Okay, so 50.2 divided by 1.8. All I did in my calculator there was I went 50.2 divided by 1.8 and I changed it to a fraction. So 251 over 9. And now I'm going to convert that to degrees. So I multiply by 180 over pi. And that gives me, when rounded to the nearest degree, 1,598 degrees. Okay, 1,598 degrees. Determine the radius of a circle if an arc length of 12 centimeters is subtended by an angle of 3 pi over 4. Round your answer to the nearest centimeter. So this time I don't know the radius. I've been given the arc length and I've been given the angle, and I have been given the angle in radians, so I don't have to convert that. So I plug in everything I know, and I'm just going to solve for what I don't, okay? So essentially, I'm going to go 12 divided by 3 pi over 4, and that'll be r, okay? Ends up being 5.1. Okay? All right. A child's lollipop is in the shape of a rainbow. Calculate the perimeter of the lollipop, given the measurements shown. Round your answer to the nearest tenth of a centimeter. So a couple things you need to understand in this question. First of all, you need to understand what perimeter means, okay? Perimeter is the distance all around an object. So I'm actually looking for this, plus this, plus this, plus this, okay? Now, I know these straight pieces are 3, so that's half the battle right there. I've got a 3 on that side, I've got a 3 on the other side. But the other two guys are arc lengths, so we're gonna actually have to calculate this large arc length and this smaller arc length, okay? So I need the arc length from here to here, which actually means I need the angle that goes from there to there. I've only given you half of that. I gave you pi over 4. But that means that the other guy would also be pi over 4. And so altogether, I'd have pi over 4 plus pi over 4, which is 2 pi over 4, or that reduces to pi over 2. Okay, so my angle in question is pi over 2. Then for the large arc length, this guy here, I would have a radius of 8 because I'd have 3 plus 5. And then for the small arc length, which is this guy here, I would have a radius of just the 5. Okay, so I've got 3 plus 3. If I'm solving for arc length, that would be, if I just rearrange this to solve for arc length, that would be theta times r, right? So I'd have pi over 2 times 5, and I'd have pi over 2 times 8, because one of them, the radius is 5, and one of them, the radius is 8. Okay, so that's everything I just said. Now I just plug it into my calculator and get an answer. And you should be looking at 26.4 centimeters, 26.4 centimeters, okay? Similar question to that, this was a released item from an old diploma. The wiper on the rear window of a particular car moves through an angle of 5 pi over 6 radians in a single sweep and clears a region that is 16 inches wide, as shown in the diagram below. The total perimeter of the cleared region to the nearest inch. So again, I'm looking for perimeter. Again, that would be this plus this, okay? That little piece in here is not a clean piece, plus this, plus this. So a very similar shape to the lollipop I just showed you. Okay, I know the angle in question here is 5 pi over 6. I know the straight pieces are 16 each. Then I got to get the large arc length, and I got to get the small arc length. So the large arc length, the radius of the large arc length will be 20. You got to remember to go back to the center of the circle there, right? It's not 16 here because that's not to the center of the circle. 20 would take you back to the center of the circle. Okay, so I would have 5 pi over 6 times 20 for the large arc length. And then for the small arc length, I'd have 5 pi over 6 times 4. So I have 5 pi over 6 times 4 plus 5 pi over 6 times 20 plus 16 plus 16. Okay, when you put all that in your calculator, you should get an answer of D, 95 inches. Okay, D, 95 inches. All right. So now we'll talk a little bit about angles in standard position. A lot of this got covered in 20-1 and then just reiterated in 30-1. An angle in standard position is a rotational angle placed on the Cartesian plane such that its initial arm is on the positive x-axis, its vertex is on the origin, and its terminal arm is in one of the 4 quadrants. Positive angles refer to a counterclockwise rotation, and negative angles refer to a clockwise rotation, okay? Okay, so vocabulary you got to be okay with. Coterminal angles share the same terminal arm. They are multiples of a full circle in rotation away from each other. Now, so things like 30 degrees and 390 degrees are the exact same thing, because if I'm at 30 degrees, I could add a full circle to that. So here I am at 30 degrees. I could add a full circle to that, which is another 360, and I'm right back to where I was. So 390, these guys would be coterminal, okay? I could subtract a circle, which would be 330 minus 360. Well, that would give me negative 330, okay? Also coterminal, and I could do that forever and ever and ever and ever, okay? The principal angle is the smallest positive coterminal, and often that's the one we want to try and figure out ratios with. So for these 3 examples that I gave you, although they're all coterminal, the principal angle would be the 30 degrees, okay? And then the reference angle is the quickest way back to the x-axis. It is an acute angle. It has to be less than 90 degrees, and it's always being formed by the terminal arm and the x-axis, okay? Okay, so we're going to fill in this table together and see what we can come up with. The coterminal angle is 430. I want the principal angle. Well, if I want the principal angle, I'm just going to minus 360 until I can't minus 360 again without going negative. So that's probably just going to be one circle there. If I minus 360, 430 minus 360, I end up with 70 degrees. Okay, so that tells me I'm in quadrant 1. And it also tells me that my reference angle is 70 degrees. Reference angles are the same as the actual angle in quadrant 1, okay? All right, principal angle is 330. If I want a coterminal angle, well, I'd have to either add 360 or subtract 360 from that. Okay, so if I added 360 to that, that'd be 690. If I subtracted 360, I'd be at negative 30. I'm in quadrant 4 for that, and my reference angle would be 30 degrees. There's 30 degrees back to the x-axis there. Okay. Okay, I'm in quadrant 3 with a reference angle of pi over 3. Well, if I'm in quadrant 3 and I have a reference angle of pi over 3, I know that this is pi from here to here. So I'm just going to call that in my head 3 pi over 3. So I have a common denominator. 3 pi over 3 plus pi over 3 is 4 pi over 3. Okay, so my principal angle would be 4 pi over 3. Now, a coterminal angle to that, well, I just add 2 pi or subtract 2 pi. Now, again, just think about 2 pi as a fraction over 3. That would be 6 pi over 3, because 6 over 3 is still 2. Okay, and the reason I'm doing that is because then the mental math is super easy, right? I just add 6 pi over 3, and that gives me 10 pi over 3. Or I subtract 6 pi over 3, and that would give me negative 2 pi over 3. So either one of these guys would be coterminal to the 4 pi over 3. Okay. Then I have a principal angle of 3 pi over 4. That's going to put me in quadrant 2 with a reference angle of pi over 4. And for the coterminal angle, I will add 2 pi or subtract 2 pi, but this time I'm looking at a fraction over 4. So that'd be 8 pi over 4, because 8 over 4 is 2. So 3 pi over 4 plus 8 pi over 4 is 11 pi over 4. Or 3 pi over 4 minus 8 pi over 4. That's just me adding or subtracting 2 pi. What's that? Negative 5 pi over 4. Okay. All right. See, this is fun. We got this, man. Okay. Given that the point negative 3, 4 lies on the terminal arm of an angle theta drawn in standard position, determine the 6 trigonometric ratios. Okay, so you draw a picture, you're in quadrant 2, you're going to draw up a perpendicular so that you got a cute little triangle from your terminal arm, and you're going to figure out the 3 sides. So you know the base of this triangle right now is negative 3, the height of this triangle is 4, and then you can Pythag your way to the hypotenuse, 3 squared plus 4 squared, then square root it, you'll get 5. Okay. Now, the 6 trigonometric ratios. So I've got sine, cosine, and tangent, and then I've got their reciprocals. The reciprocal of sine is cosecant. The reciprocal of cos is secant, and the reciprocal of tan is cotangent. And those are written on your formula sheet for you. Okay, so sine would be 4 over 5 because it's opposite over adjacent. Now, I was getting lazy there. You should always make sure you're writing sine of theta, not just sine, right? Sine is nothing in and of itself. So sine of theta equals 4 over 5. The cos of theta will equal negative 3 over 5. And then the tan of theta will equal negative 4 over 3. Okay, put your negative in the front or put it on the top number. Never leave a denominator as negative. It's just kind of bad grammar. So then we have the cosecant of theta, which would be the flipped version of sine. So if sine is 4 over 5, cosecant of theta is 5 over 4. Then we have secant of theta, which is the flipped version of cos, so that'd be negative 5 over 3. And then we have cotangent of theta, which would be the flipped version of tan, which would be negative 3 over 4. Okay, so question, why are some of these ratios negative and some positive? Well, it all has to do with what quadrant you're in and whether x is positive or negative in that quadrant and whether y is positive or negative in that quadrant. And I'm hoping at some point your teacher, your grade 12 teacher, talked to you about the CAS rule. Okay, some kids call it the CAS rule. Some kids use the acronym all students take calculus, whatever works for you. What this is telling you though is who's positive in what quadrant. So for quadrant 1, all ratios are positive. In quadrant 2, only sine ratios are positive. The cosine and the tangent would be negative. Now, when I say only sine ratios are positive, I'm also saying that cosecant is positive, right? Because when I flip sine to make it cosecant, that doesn't change negativity. So when you see sine is positive, sine and cosecant would be positive, okay? In the third quadrant, tan and cotangent would be positive. And then in the fourth quadrant, only cosine and secant would be positive, okay? So if tan of theta is negative root 3 over 5, and I'm somewhere between 90 degrees and 180 degrees, determine the exact value of the cos of theta, the cosecant of theta, and the cotangent of theta. Also determine theta to the nearest degree. So again, you want to draw a picture. This is super visual. You want to make sure you're staying very, very visual. I know I'm in quadrant 2 because theta had to be between 90 and 180. And that makes sense because tan would be negative, okay? So if I put myself in quadrant 2, I know that tan is opposite over opposite over adjacent. So I know my opposite is going to be root 3 and my adjacent is going to be 5. One of them has to be a negative. In the context of this question, it would have to be the 5 that's the negative because x is negative in quadrant 2. Okay, now I'm going to Pythag my way to the hypotenuse. So negative 5 squared is 25, root 3 squared is 3, 25, and 3 is 28. So the hypotenuse is going to be the root of 28, which I would then want to reduce, or simplify, I guess I should say. That's 4 times 7, so that'd be 2 root 7, okay? Okay, so now you were asked for a cosecant. Cosecant would be negative 5 over 2 root 7. Now we'll have a quick conversation around rationalizing, okay? In 20-1, you would have always been told your answer has to be in rationalized form. In 30-1, it actually doesn't have to be in rationalized form. You can leave it like that, and that is acceptable as long as the question didn't state write your answer rationalized, okay? If the question never stated write your answer rationalized, you are perfectly fine to leave it like that, okay? Your diploma will actually go back and forth between rationalized answers and non-rationalized answers. So you just have to be comfortable understanding that if you have it rationalized and the diploma didn't have it rationalized, that you know they're the same thing, okay? If you're going to rationalize this, you would multiply by root 7 over root 7, and that would give you negative 5 root 7 over 14, okay? Then I asked for the cosecant of theta. Well, cosecant of theta is the flipped version of sine. So if sine is root 3 over 2 root 7, cosecant of theta will be 2 root 7 over root 3. Again, be perfectly okay to leave it like that, but if you want to rationalize it, you'd have to multiply it by root 3 over root 3, and that would give you 2 root 21 over 3, okay? And then we have cotangent. Cotangent is the flipped version of tan. So if tan is root 3 over negative 5, cotangent would be negative 5 over root 3. And then if you want to rationalize it, that would be negative 5 root 3 over 3. Okay. Now, you are also asked to get theta. What you're going to do to get theta, this is when you're going to have to arc sine or arc cos or arc tan, otherwise known as the inverse or otherwise known as your second function button of sine, cosine, or tangent, okay? I'd love it if you remember to say arc sine, but at this stage of the game, I just need to make sure you can get to the answer. Okay, so what you do though is you always ignore the negative sign. Always arc tan or arc sine the positive, and then that will always give you the reference angle, okay? So take note of how I'm communicating here. I said, okay, tan of theta's reference angle is root 3 over 5, and so that means theta's reference angle will be the inverse tan or the arc tan of root 3 over 5, and that should give you 19 degrees. This is an important moment to make sure you're in the right mode for your calculator. The mode of your calculator only matters if you're pressing the sine, cosine, or tangent button, okay? Okay, so I get and again, just notice that I ignored the negative, and that's why I'm saying I'm solving for the reference angle at the moment, okay? So I know my reference angle is 19 degrees, and I know I'm in quadrant 2, so my actual angle in standard position will be 180 degrees minus the reference angle, so 180 minus 19, and that will give me theta being 161, okay? Good. Given that tan of theta is 5 over 12, and I'm somewhere between pi and 2 pi. Well, okay, if I'm somewhere between pi and 2 pi, I am in quadrants 3 or 4, but tan has to be positive, which means I'm only in quadrant 3 right now. So you're going to draw a picture of this in quadrant 3. You know that it's super important. Lots of kids will just draw like the base of their triangle and the height of their triangle and call 1, 5 and 1, 12. That's not right because you're in quadrant 3. Both of these values are actually negative, okay? So you got to be super careful with that. Then you're going to Pythag your way to the hypotenuse. 12 squared is 144, 5 squared is 25, 144 and 25 is 169. and the square root of 169 is 13. Okay, so now I've got all my numbers ready to go. If I want cosecant of theta, cosecant is the flipped version of sine. So if sine would be -5/13, I'm just going to flip that. Cosecant of theta would be -13/5. Okay. Then if I want theta, again, I'm going to start by getting theta's reference angle. Well, I was already told that tan of theta was 5/12. So I can use that to get the reference angle. The reference angle will be the inverse tan of 5/12. And now you have to switch over to radian mode because this one asked you for radians. You always need to speak in the language you were asked, okay? Because the domain value here was given in radians, that means you have to answer in radians, okay? Okay, so that gives you 0.3948 when rounded to 4 decimal places. And now I need to think, okay, that's my reference angle. I know I've got pi all the way to there, and then I'm going to add that reference angle in quadrant 3. So my actual theta will be pi plus 0.3948, which is 3.56. 3.536. Okay? All right. Okay, so now we're going to turn our attention to the unit circle. And I am going to build the unit circle with you. What I don't want you guys to do is to try and memorize a unit circle. I find when kids just try to memorize the unit circle, they miss little details and then they memorize it wrong and then the whole thing kind of falls apart. What I want to do is I want to walk you through building the unit circle in a way that I'm hoping you understand how it works. If you understand how it operates, it's not as big and intimidating as one might think, okay? Before we get there though, we have to establish what the equation of a circle is. So the equation of a circle with its center at the origin and a radius of r can be described by x squared plus y squared equals r squared, where r is the radius and x and y are any point on the outer edge of the circle. So this would have the center at the origin and any radius. If I now want to create a unit circle, which is still the center at the origin, but it has a radius of 1, well, I just replace r with 1, and 1 squared is 1. So the equation of the unit circle is x squared plus y squared equals 1. We can use special triangles and the unit circle to help us determine exact values for various trigonometric ratios. Now, you know, there's like 16 different spots. When we build a unit circle, there are 16 different spots that we use that give us pretty trigonometric ratios, okay? What you need to understand though is there's an infinite amount of spots on the unit circle. There's an infinite amount of points all along that circle. So after we're done the unit circle, I don't want you to think, oh, okay, so there's 16 points on a unit circle. No, not at all. And actually, nobody's ever going to ask you to build that unit circle the way I'm about to build it with you. Nobody's going to ask you to do that on a diploma, okay? That's not what a curricular item or outcome of 30-1. What is the curricular outcome is you need to understand this formula and you need to know how to apply that formula, okay? So they might give you an X value and you have to figure out the Y value or vice versa. So you do need to understand that. And this equation is not given to you on a formula sheet, okay? Okay, so as we begin to build, the first conversation we need to have is around special triangles. So there are 2 different special triangles. The first is a 45, 45, 90-degree triangle. Now, when I want to go establish ratios for a triangle, what I do is I just take the side or the angle that has the smallest measure, and opposite that I call a 1. So my 45 here is the smallest. I'm going to put a 1 right there. Now, this is also 45 though, so opposite that guy will also have to be a 1, which means this ends up being an isosceles triangle. The other angle is 90, which means I have a right triangle, which means I can use the Pythagorean theorem to get my hypotenuse. So 1 squared is 1, 1 plus 1 is 2. I'm looking at root 2 for that guy, okay? Now, why do I care about this? Well, right away, it tells me that, hey, the sine of 45 is 1 over root 2, right? Opposite over adjacent. Sorry, opposite over hypotenuse. That's very, very powerful because 1 over root 2 is an exact value, okay? If you type sine of 45 in your calculator, it's going to give you 0.7071 with a bunch of other decimals there. That's not exact value. 1 over root 2, which is that number, is exact value, and that's way better, okay? So now I know that the sine of 45 is 1 over root 2, and I know the cos of 45 is 1 over root 2, and I know the tan of 45 is 1 over 1, opposite over adjacent, so that would be 1, okay? See, that wasn't bad. Okay, let's take a look at the next guy. The next guy, I'm actually going to start with an equilateral triangle. And what I'm going to do, an equilateral triangle has everything the same, right? So that would be 60, 60, 60 for my angles. And then I'm going to take it and I'm just going to cut it right in half. And if I cut it right in half, this becomes my 30. So on this left side here is what I'll work with. And that's a 30, 60, 90 degree triangle. That's my next special triangle, okay? I'm going to do the exact same thing I did. Opposite my smallest angle, I'm going to call a 1. So opposite the 30 degrees, I call a 1. But that 1 would represent half of this overall equilateral triangle side, which means if half of that side is 1, all of that side is 2, which means all of the outer edges of the equilateral triangle are 2, which means I know this guy. That guy's also 2. Now I can Pythag my way to the height of this little triangle. So 2 squared minus 1 squared, so 4 minus 1 is 3, and I get root 3. Now, again, why is that all helpful? Because now I can say, hey, I know that the sine of 30 is 1 over 2. I know the cos of 30 is root 3 over 2. And I know the tan of 30 is 1 over root 3. I know that the sine of 60 is root 3 over 2. I know that the cos of 60 is 1/2, and I know that the tan of 60 is root 3. So suddenly I get all of those exact value trigonometric functions that are super helpful, okay? Now what I'm going to do is I'm going to put these triangles inside a unit circle, okay? So what we're going to do to start is just look at the first quadrant of the unit circle, and we're going to divide a unit circle into kind of 3 sections. The first one will be my quadrantal angles. Quadrantal means I'm on the axis, so like your 0, 90, 180, 270, and 360. Then I'm going to add in 45-degree lines, and then I'm going to add in 30-degree lines. Okay, and I'm going to show you that the unit circle, when you do it that way, is not big and intimidating at all, okay? But there's just a little bit more background. If you can really get an understanding of quadrant 1, the rest of the unit circle is not hard, okay? So let's just focus on quadrant 1 for a second. So what I want with each of these is I want us to be able to establish what angle we're at in degrees, what angle we're at in radians, and then what the coordinate point on the outer edge of the circle is, okay? So if I just go up in degrees, I've got 0, I've got 30, 45, 60, and 90, okay? Now with radians, I'm gonna kind of ignore where the radians come from just for a second, because we're gonna have a much easier time with that when we're looking at the full circle, okay? But I'll just give them to you for now. This is 0 over 2 pi, pi over 6, pi over 4, pi over 3, and pi over 2. Okay, now where I want to focus this next bit of conversation is around getting the coordinate points. Well, this one's easy because I knew that I have a radius of 1. So I know that this has to be the point 1, 0, and I know this has to be the point 0, 1. Okay, whoops, I did not do it that way. Huh, I'm going to hide that on you. I know that this has to be the point 0, 1, but obviously I'm going to show that to you in a minute. Okay, so let's just pick on that 30 degrees for a second. And watch what I'm going to do here. I'm going to drop a perpendicular for a sec, right at that edge, okay? So I drop a perpendicular. And what I notice now is I have a 30, 90, and the leftover bit is 60. So I have a 30, 60, 90 degree triangle here. Awesome. Well, I know that the ratio for my 30, 60, 90 degree triangle was 1 and root 3 and 2. Okay, super cool. Here's the problem. That doesn't fit on the unit circle because the unit circle has a radius of 1. Right now, the way I labeled this triangle, my radius is 2. So it's actually too big. It actually would be sticking out of the unit circle. So I want to shrink this triangle down so that it perfectly fits inside the unit circle. I need to make that 2 become a 1. And the way I do that is I divide by 2. I just cut all my dimensions in half. Okay, so if I was to cut all my dimensions in half, I just want to switch colors here for you. This would become a 1. This would become a 1 over 2 because I'm dividing everything by 2. And this would become a root 3 over 2. So now to get to this point on the outer edge of the circle, I would have to go over root 3 over 2 and up root 3 over 2. Okay, so I go over root 3 over 2 and up, I'm sorry, I said root 3 over 2, up 1/2. I should listen to what I'm saying, sorry. Up 1/2, okay? Now, two super important things that I want to talk to you about before we keep going here. Number one, you just found the actual coordinate point on the edge of the circle when my terminal arm has been rotated 30 degrees, okay? Super. Who cares? Well, this is why we care. If I was to ask you for the sine of 30, you would go opposite over hypotenuse. Or in this case, it's the y value over the hypotenuse, right? But the hypotenuse is 1 because it's the radius. So it ends up being the y value over 1, which just ends up being the y value. The reason we like the unit circle is because they're actually telling us, hey, that's the sine of 30 right there because it's y over 1. Okay, same thing for cos. If I wanted the cos of 30, I would go my x value over 1. So this guy here is the cos of 30. So every coordinate point that we have on the unit circle is actually going to be cos of my angle and sine of my angle. Okay, so just remember Calgary Stampede, cos comes first, C and then S. Calgary Stampede, okay? Cos is your x value, sine is your y value. Okay, awesome. So we got that guy done. Whoops, I just need to take my ink off here, sorry. Now we're gonna have the same conversation around the 45 degrees. So first thing I'm gonna do is I'm gonna drop a perpendicular, okay? And then I know that I have a 45, 45, 90 degree triangle. So I've got 45 degrees here, and I got 45 degrees here, and I got my 90 degree triangle down here. I know that the ratio for that is 1, 1, root 2. Whoa, that was a big root. Okay, but that doesn't fit in my unit circle because root of 2 is like 1.4 something or other. Still too big. So I want to shrink it down, and I'm going to shrink it down by dividing everything by root 2 because root 2 divided by root 2 will just give me the 1, and then that will fit perfectly inside my unit circle. Okay, so that now gives me the actual coordinate point right here. If I want to go to that point, I'd have to go over 1 over root 2 and up 1 over root 2. Okay, now I'm going to rationalize that and call that root 2 over 2 because I'm old and I just always do that. But you can do it either way. Okay, so that's the point, root 2 over 2, comma root 2 over 2. Now, you now know that the cos of 45, because cos is your x value, cos of 45 is root 2 over 2. And you know that the sine of 45 is also root 2 over 2. Okay, all right, so now I know that guy's done. Then we look at 60 and we realize that 60, if I drop a perpendicular in that, I'm going to get, well, I'll do it here for you. So if I drop a perpendicular, I know that this is 60 here. And I know that this is now going to be 30 up here, which is just the flipped version of the 30 at the corner and the 60 at the top that I did at 30 degrees, which means the x and y value have actually switched places, which means I'm going to get this coordinate except flipped. So it's now going to be 1/2, comma, root 3 over 2. Okay. And then the last guy I talked about was 0, 1. I had already mentioned that one. So if we're looking for the sine of 30, we know that it's opposite over hypotenuse, but what's the length of the hypotenuse? Well, the length of the hypotenuse is 1. That's why we're talking about the fact that the x value is the cos of that angle, and the y value is the sine of that angle, okay? Okay, let's go through the unit circle now. We're gonna build it. I'm going to shut me off just because it's going to get a little messy here. So you'll just hear my voice as we build it. Okay, so when we go to build the unit circle, I essentially want to do this in 3 different rounds, okay? The first round that I'm going to do, I'm just going to look at these quadrantal angles right here, okay? And remember that you are looking for the degree measure, the radian measure, and then the coordinate point as well, okay? And this is a fairly straightforward first go around. We know that, well, first of all, let me just state who's positive and who's negative in each quadrant here. Okay, so I've got positive, positive, negative, positive over here, negative, negative, and positive, negative. Now, we know for degrees that this is 0, 360, I've got 90, I've got 180, and I've got 270. For radians, I think we're pretty confident to say that this guy's 0 and 2 pi. I'm hoping we're decently confident to say that that guy's pi, which means this guy here, where I'm 90, that has to be halfway between 0 and pi. Well, that would be half pi. So that's what I've written. And then down here, this guy here would have to be halfway between 1 and 2. Well, halfway between 1 and 2 is 1.5. As a fraction, that would be 3 pi over 2. Okay, and then as your coordinate points, we've got 1, 0 here, and we've got 0, 1 here, negative 1, 0 here, and 0, negative 1 down there. Okay, so that's the first go around. That's all you had to do. Not bad at all. So what do we know now? Hey, we know that the cos of 180 is -1. Go in your calculator, make sure you're in degree mode, and see that the cos of 180 is -1. We know that the sine of 180 is 0. Check that out, okay? Every coordinate point that we do, the x value is going to be the cos of that angle, and the y value is going to be the sine of that angle. Okay, now go around number 2. We're going to take a look at the 45-degree line. So I'm just going to focus on these red lines right here, okay? And what we do is as we go around, we just keep adding 45 degrees. We always include the purple axis that I've already have there when we're doing this, and that's how this is going to make our life much easier, okay? Okay, so just let me clear that highlight off. Okay, so we've got 0 plus 45 is 45. Plus 45 is 90, plus 45 is 135, plus 45 is 180, plus 45 is 225, plus 45 is 270, plus 45 is 315, and then plus 45 is 360. Now, take a look at radians for a sec, okay? I have to go 1, 2, 3, 4 steps to get to pi. If I have to go 4 steps to get to pi, every step is pi over 4. So all I actually have to do to go all the way around that circle is count to 8. I'm going to go 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. But as I do it, I'm going to reduce the fractions as I go. Okay, so I start with 0, and then I add pi over 4, 1 pi over 4. 2 pi over 4 reduces to pi over 2, and it's already there. 3 pi over 4. 4 pi over 4 reduces to pi, and it's already there. 5 pi over 4. 6 pi over 4 reduces to 3 pi over 2, and it's already there. 7 pi over 4, and 8 pi over 4 reduces to 2 pi, and it's already there. Okay, we've already established that we've got root 2 over 2 comma root 2 over 2 as the point here. Every one of these red guys have the same 45-degree reference angle. So all of them are actually going to be root 2 over 2 comma root 2 over 2. It's just that you have to take into account who's negative and who's positive based on the quadrant that you're in. So in this guy, your x is negative, but your y is positive. In quadrant 3, they're both negative. And in quadrant 4, your x is positive, but your y is negative. Okay, and that was the second go around. Now we need to go the third go around, which I'm going to look at the blue lines. And remember, so yeah, I'm going to ignore the red lines, but I'm not going to ignore the purple lines. I always count the axes as I'm going. So the blue lines are essentially, you just add 30 degrees every time. So 0 plus 30 is 30, plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, plus 30 is 180, plus 30 is 210, plus 30 is 240, plus 30 is 270. plus 30 is 300, plus 30 is 330, and plus 30 is 360. Let's count how many ways we go to pi. So 1 step, 2 step, 3 step, 4 step, 5 step, 6 step. So each step will be pi over 6, which means I have to just count up to 12 on this guy, okay? Okay, so starting here, we've got pi over 6, then 2 pi over 6, but 2 pi over 6 is going to reduce to pi over 3. Then 3 pi over 6, but that reduces to pi over 2, and it's already there. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 doesn't reduce. 6 pi over 6 is pi. 7 pi over 6 doesn't reduce. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2, and is already there. Remember, I'm just counting to 12, right? 10 pi over 6 reduces to 5 pi over 3, and 11 pi over 6 doesn't reduce. And then 12 pi over 6, I'm back to the 0, 2 pi. Okay? Now, I've already established what the coordinate points are. I knew root 3 over 2, comma 1/2, and I knew 1/2, comma root 3 over 2. All of the over 3s and all of the over 6s share the same reference angle. So these guys here are all the over 3s. They will all be the same coordinate point, just with the proper negativity on x or y, depending on the quadrant that you're in. And all the 5 over 6s will have this point. Sorry, all the over 6s, I shouldn't have said I was looking at the 5 pi over 6. All the over 6s will have this point here, and it'll just depend on who's positive and who's negative. Okay, so I'm just going to add in the rest of those guys. And you can check yourself as well and make sure you've got them all down right. And that is the unit circle. Okay, now I get that that's pretty big and scary and intimidating when you first look at it. Okay, but what I want you to see, and what I'm hoping you've seen as we've gone around it 3 different times, is it's not as intimidating if you just take it chunk by chunk and step by step and you understand how it's being built. Okay. All right, so a couple of questions on this guy then. Point A, xy, is the intersection point of the unit circle and the terminal arm of 145 degrees in standard position. The coordinates of point A to the nearest hundredth are. Well, we just said every coordinate on the unit circle is cos of my angle, comma, sine of my angle. So I just have to figure out what the cos of 145 is, and that's my x value. And I have to figure out what the sine of 145 is, and that's my y value. Okay, so you should be getting an answer of C there, an answer of C. Okay, the point -4, 5, sorry, -4 over 5, comma y lies in the third quadrant of the unit circle. Determine the value of y. So we're just going to plug in -4 over 5 for x into our equation. X squared plus y squared equals 1. Let's do this without a calculator because we can. You can do this. -4 over 5 squared. Well, that's squaring the top, squaring the bottom. That'll be 16 over 25. Now I'm going to have to subtract 16 over 25 from both sides. Well, let's call my 1 25 over 25 then. So I have a common denominator there. 25 minus 16 is 9. So I end up with y squared equals 9 over 25. And then I'm going to square root it. Well, if I square root that, that will end up being y equals plus or minus 3 over 5. Now I need to think about the fact that I'm in the third quadrant. And if I'm in the third quadrant, is y positive or negative? Y is negative. So my final answer will be y will be -3 over 5. Okay. All right, good. So now let's use the unit circle to find the exact value of the following. So cos of 3 pi over 4, I can just go right to the unit circle you just built. I'm looking at the x value, pardon me, I'm getting -√2 over 2. Tan of 11 pi over 4, well, that's actually larger than a full rotation, so you want to get a principal angle first. Essentially, you're just going to subtract 2 pi from there. So if I think about 2 pi as a fraction with a denominator of 4, so I have a common denominator, that would be 8 pi over 4. So 11 pi over 4 minus 8 pi over 4 would give me 3 pi over 4. So really, I'm looking for the tan of 3 pi over 4 here. That'll be the same ratio. Okay. Okay, so I go over to 3 pi over 4, which I was just there. Tan would be the y value divided by the x value because it's opposite divided by the adjacent, okay? Even on your formula sheet, it tells you that tan of theta is sine over cos. So even if you remember that sine is your y value and cos is your x value, then you're good to go. The other thing I wanted to share with you, just while we're talking about that, because I don't know why this is never taught to you in junior high, but so just so that we have the visual of where you are, you're right here right now. This is negative root 2 over 2 comma root 2 over 2. And I'm going to divide y by x, okay? Now, this one's pretty easy because you're looking at this and you can see that they're the same thing anyway. And you're like, okay, well, anything divided by itself is 1. So my answer is going to be -1, and I get that. But what I want to share with you is when you're dividing fractions that have common denominators, you just divide the numerators. So you could look at this as root 2 over negative root 2, and then that's where you can get your -1. That's super helpful when you have other ones like, say you were looking at root 3 over 2 comma 1/2, and I want the tan of that. Well, right away, I just know it's 1 over root 3, okay? Because my common denominator is there already. If I have a common denominator, I just divide the numerators, okay? Okay, cool. Then sine squared of 5 pi over 6. What that means is find sine of 5 pi over 6 and then square it. The sine of 5 pi over 6, I'm just going to my unit circle, is 1/2, and 1/2 squared is 1/4. Okay. Awesome possum. Okay. 2 points are drawn in standard position as shown. Determine the measure of angle theta. So what I want you to look at is I would want you to see that these are both coordinate pairs from the unit circle. Okay. So then there's a couple different ways you could look at this. I actually just put in the reference angles right away. I said, okay, that has to be 30 degrees and that has to be 45 degrees. Some of you may not look at that as 45 degrees, and instead you might look at this whole thing from there to there as 135 degrees, and that's totally fine too, okay? So I went 180 minus 45 minus 30. Maybe you went 135 minus 30. Doesn't matter. You're going to get the same answer no matter how you do it. And the answer would be 105. Okay. All right. So that finishes up our introduction to trig. From here, the next thing we'll deal with is the graphs and transformations on trigs. Okay. So I will see you there. Take care.